So where the industry is moving towards and how it is going to impact the future developers as of now. So in this regard, just before going to that aspect, so we had talked about the website where you can have the OpenCL resources, which includes the OpenCL tutorials, video presentations, the sample programs, the toolkits, the profilers, debuggers, right? Then the OpenCL University Toolkit. So all of them can be downloaded from this site. Okay? Just you have a small simple registration and followed by which you can just go and download it, right? So what I'm going through is in this session, just I made a small points, bullets, and since OpenCL is vast, so what I try to make is to get a feel how an OpenCL programming would look like, and just get a hand on how you can use it and you are comfortable to use it. Probably then you can go to that site and explore further. That's what the scope is all about, right? So in this regard, these are some of the initial bullet points. How the supercomputing components are moving into the desktop computing. That's what we will be discussing. Then, what is the OpenCL platform model, OpenCL architecture with the memory scopes, and OpenCL memory alignment with the process model, and a sample OpenCL APIs. And followed by a list of examples to go with. Then we'll have a small demo of how you can use the different tools like code analyzer, functional analyzer, and followed by which you should have an end-to-end view of how and where these tools are getting used, or how you can use these tools for a different point of programming. Then I'll just give a simple sample IEEE publication of results, which is on the OpenCL usage, and the final takeaway. As far as the students, what is the takeaway, and for the faculty. And in conclusion, we'll have a small Q&A on that. Okay, to start with, as I said, we'll start off with a simple fact, the why OpenCL has come into it. This is just a small timeline and history. So the supercomputing components are getting or moving into the desktop computing. So if you go back to late 80s, early 90s, probably if you buy a box, the computing unit, you'll come to know that there was something like CPU, fine. For mathematical calculations, they had a separate chip, simple. That's called a mathematical coprocessor, math coprocessor. It was a separate chip. So, any mathematical operations, complex things, sine, cos, that used to go there. Later, what happened? Now in current systems, do you have a math coprocessor? Yeah, it is fused. It is fused into the processor, right? Okay. So what happened is, as the technology improved and fine-tuned, you got fused. So your IN computing unit is now part of a CPU, right? Likewise, there were some supercomputing models like Cray. Cray is one of the known supercomputing device or model. So they are very famous for one thing, that's called vector engines. So what is vector engines? Okay, what is vector processing or vector engines? Vector is nothing but, as I put in simple words, is you have a bunch of data as you are doing the same operation on all of them in the same clock cycle. Okay, so the one best example is single instruction, multiple data, SIMD engines. So these SIMD engines were designed in the Cray vector engines. So that slowly moved into the CPU part. Now if you cut open your CPU part, do you find SIMD engines? Yes, we have SIMD engines, right? So that means whatever happened for supercomputing is now getting slowly merged into desktop or moved into desktop computing. Likewise, multi-processors were there. Now what do you have? And we are here today for multi-core programming, right? Now if you cut open a CPU processor, you have multi-cores aligned, right? So that is also initially was part of your supercomputing. Likewise, you have something called NUMA architecture. So what is NUMA? Non-uniform memory access. So if you have multiple cores or multiple processors, so you have each processor having its own local memory. So if there is one processor, if you want to access another processor local memory, so the timing is always non-uniform, right? So that part is also moved into a desktop computing. So the next thing is what? Okay, the next thing is the heterogeneous computing. To give a simple example, what is the fastest supercomputing computer available now? Anyone? Okay. The fastest supercomputing is in China, that is Taiwan 1. Okay, its equivalent name is Milky Way. It can compute at the rate of 2.57 petaflops per second. Okay. So what's so interesting that got to do with our heterogeneous computing? The point is the supercomputing machine is built on GPU, General Purpose Graphics Processing Unit. So it contains, say, thousands of CPU plus another set of thousands of GPU parallelly working to achieve that 2.57 number, right? So what is that? Can't we do that with our using just CPUs? I'll tell you, if you are doing the same thing, if you were trying to achieve the same 2.57 number using just CPU, what happens? Right? Forget about GPUs. Just take 2.57 numbers. Get that. So if you are trying to increase the number of CPUs and get that number, the power consumption, okay, will be around 12 megawatts. 12 megawatts of power is consumed to get that number. Now what happens? You may ask this next question. Are we not having the same power advantage consumed for CPU and GPU together? Right? So because of the CPU and GPU capacity, the power consumption is just 4 megawatts. 8 megawatts you are saving. Okay. So you have seen in India, right? In India, there are micro power generation units which generates say 1 megawatts or 2 megawatts, which powers a few villages. Remember? So now you just you can make out the difference. So you may ask, how is that only CPU is covering that much power, and why GPU and CPU is reducing the power consumption? To answer this question, so earlier one person had asked, what is the frequency of GPU? Why? See, CPU is somewhere in terms of gigahertz, but it is not able to deliver that much calculation power that of a GPU. So to answer that, see, the GPU operates at a lesser frequency, maybe 500 to 750 megahertz only. The only difference where it happens is the number of engines, number of calculation or the number of engines. It's very simple and simple architecture where you have number of SIMD engines placed tactically controlled by a single decoder. So for one clock cycle, if there are 20,000 SIMD engines, one clock cycle applied, it calculates and gives out the result. Right? Apply the same clock cycle for the CPU, only one instruction is executed. You got the difference? So this makes the heterogeneous computing the next part of or the future. That's what we are seeing. So just I wanted to give you the feel why we are actually going and where we are actually going. So why this heterogeneous computing or general purpose GPU is very important, and how OpenCL plays the role of the bridging the programming aspects for GPU. Okay? So till now we have just talked, we have talked about only GPU or graphics processor and programming that. OpenCL is much more than programming a graphics processor. If you cut open the box, you can find a lot of accelerators, audio accelerators, video accelerators, or whatever, DSPs, right? There are so many chips embedded in your machine. Each has its own capabilities. So you can actually get the OpenCL. The OpenCL actually gives a platform to pull out all these devices, program them, and use it for your purpose. It is not only GPU. So OpenCL is much more than that, right? You can actually do a parallel programming for only CPU, or only for GPU, or tie both CPU, GPU together and do a programming, or DSP, three of them together, do a programming. So it is that flexible. So I think it is the next thing to think about in terms of programming. So that's about the simple part for the history timeline and the way we are focusing. So before going to the next part, do you have any queries or solutions or questions to go with? Then, to start up with the OpenCL programming aspect, you should understand how, just now I said, we can program DSPs, graphics processing unit, the CPU, a different architecture, any device. So in that case, all of them has their own architecture, they have their own instruction set, and the way they operate is totally different. Then how do you program. For a programmer, it becomes a nightmare, right? To know all the architectures, all the devices, so it's very difficult to go with. So OpenCL gives a platform model. First, we can understand the platform model so that you can easily understand the next stages. This is a simple platform model. It contains if you cut open your CPU box, okay? Now you have to try to visualize how an OpenCL programmer sees the CPU inside the system. Forget about the architecture differences. You don't worry about the architecture difference or what capabilities. You don't need to worry about anything. So what you do is you just cut open the box. So what you say is this is the host. Host in this case is your CPU. Okay, you take any CPU for that matter. Then assume you have one graphics card. Okay, so one graphics card. So it becomes one compute device. So if you have two graphics cards, two compute device. So I have another DSP, that is another compute device. Okay, another isolator. So each of the devices becomes a OpenCL compute device. That's a convention. Okay, so again, the compute device is, if you cut open the compute device, okay, take an example of a processor, right? Take an example of a processor. So you have a multi-core processor. So you cut open processor, you find number of cores, right? So each core becomes a computing unit. Okay, so each core is a computing unit. So in the graphics also you can have multiple computing units. Fine. Then if you cut open the cores, okay, if you cut open the cores, you find some adder circuit, some multiplying circuits, or some SIMD engines, right? Or vector engines. So each becomes a processing element, right? So now what we have, a compute device, the compute unit, and the processing element. So inside that it is controlled by a host. The next question is, can the host becomes a compute device? Yes. OpenCL allows, because the host is also a computing device by itself. So you can bind an CPU as a computing device. So this is about how the OpenCL sees each of the modules of the computing unit. One is simple, remember, computing device, computing unit, and the processing element. So that's about the way the hardware is stuff. Now we will see the architecture with how memory scopes are defined. So how do you scope the memories? As simple as that. So to keep it simple, as OpenCL is, if you have written a program in OpenCL, it is guaranteed that it should run without any fault or zero fault on any other architecture, OpenCL compliant architecture, without the performance. Performance we are not guaranteeing it, but the functionality will not be broken. If that is the case, then your memory way of laying out the memory is very crucial, right? Say you have the global memory, local memory, shared memory. Some device doesn't have the shared memory. Some device doesn't have a cache memory. So if you take a processor itself, some cache will be 2 MB, some cache will be 4 MB, some will be just 1 MB, 512 KB, right? So it's lot of architecture changes are there. Then how do you cope with all that? So to mask everything. So they have come up with its generic architecture, like the previous one, like the OpenCL compute device. They have come with a generic memory model. The simplest of model is, so you take a graphics processor, a simple graphics processor. A graphics processor has its own RAM. So if you take some high-end graphics card, you can get up to 2 GB or 4 GB of RAM packed in that. Okay. So that part that RAM, you can call it as your global memory for that compute device. Okay. Global memory for that compute device. So you have one full-fledged global memory which is accessible for the compute device. Then you have something called the cache. We'll just keep the cache right now. So when we said the compute device cut open, what you get? Compute unit. So compute units will have a local memory defined. This is the way they are defining it. So you have multiple compute. You take one compute unit, you have one local memory for that. So in each of the compute unit, you can have a series of private memories. Simple. Okay. So each, say for example, one example real life example I can quote is, take the processor. Okay, that's a compute device. Then cut open, you get a multiple cores. That's a compute unit. So between the cores, I can place some cache. Between the cores, I can place some cache memory. That becomes your local memory. Okay. When you cut open the cores, you find say some vector engines. Say you have some registers. Simple. I will not say vector engines. I will say some registers are there. So that registers becomes private memory. Okay. See, the registers are memory, right? So that is operated by some adders or some. So that adders becomes the processing element, but the registers are private memory. So this is how it is being laid out. This is the memory architecture. So global memory is shared by all of the compute units. Okay, but the shared memories for a given compute unit, and within the processing element you have the private memory.
What will be the size of these memories?
Okay, that's a good question. It depends on your architecture. As of now, if you are writing a program, right now I am explaining in generic terms, so I am not fixing any value for each of them. But if you are programming for a particular architecture, so you know that okay, this architecture has 4 kilobytes of cache. So it is best to tune the application with 4K pages. So if you know that information pre-hand, I can just say 4K pages. Okay. If you are not having that information, the next question is, what should I do? So what I do is I will set an arbitrary page of 8K bytes or 8K pages. So will it work? It will work. The reason is, this is a generic model. You are not assuming to fixing to any of the architecture. So that means for 8K page size, it will surely work, but it will work slowly. What happens is, so this, okay, assume this is the 4K cache. So here, right now you don't know the information, you made 8K cache. So it can fit only 4. So now the 4K is split into 2K. That's 2 times. The first 4 is put here. The second 4 is put into this. That is the responsibility of the OpenCL platform. So you don't need to worry about that. You may not get the performance, but your program will run. Okay. So to add to this point, that was a good question. See, for example, you have OpenCL, you have an hardware, you are planning to develop your own hardware, and you know the specifications, but you don't know whether it works or not. So in that case, OpenCL gives a very good tool, such a way that even, which is the hardware which is under production, or which is under the development, not production, which is under development, can be also tested without having actual hardware. How? You can fix 4K size and still test it. Later, when the hardware comes out, you can take the same program without any changes, run it, and see the performance. So it's that way it works. So next is, so the first we saw the hardware, generalizing the different compute units. Then we saw different memory models, how it can be, how each of them are been tied up. Next is, see, who is going to use the memory? The process, right? You should have the process to access all of them and go and use particular compute units. To do that, see, now you have to visualize something. You have a compute unit. Okay? Just cut open, you get compute devices. Again, cut open, you get processing elements. Right? So processing elements are more in number, but compute devices are less in number. And compute units are less in number, and compute devices still lesser. Right? So don't you think that has become a hierarchy? Hierarchy, it's like a tree hierarchy. Simple. So, if you see the, if you go to any industry, you find manager.
Organization chart.
Sorry?
Organization chart.
Yes. Take an example of your, go to any industry, the management organization chart is like director, group of managers, then you have people who are under them working them actually. So, now the OpenCL process is exactly categorized in the same format. So here they call it as ND space. ND is n-dimensional space. It can go to, say it's like a matrix format. Say each processing element is tied as one work unit. Okay? So you can like this. So each processing element will be one work items. So that is using its own private memory. That is grouped under a work group. Okay? That is using, so the work group is your compute units. Okay? So that is a local memory. Then you have the compute device, so under which you can have a group items falling into place. So it is like this. Set of threads, okay, threads having a thread IDs grouped into a master thread, and that again falls back to a unit. It is the same stuff. Only thing is, if you want to access a particular work item, we call it as ND space, that is n-dimensional space. You require X, Y, Z, the coordinates. So that is used for identifying the particular thread. Or we will not call it a thread, we call it as a work item. Okay. So is this clear? So before going to the next part, do you have any queries here? It is very, this part should be very clear. Then only you can understand how the programming actually goes about, or you can do the program. So OpenCL platform is like this: compute device, the compute units, and the processing elements. Then you have constant global memory. Then you have the local memory and the processing element having the private memories. Here, work item, work group. A work group is group, and each of them is accessed through ND, n dimensional, the coordinates ijk. So, any queries on this?
Sir, is it OpenCL is going to support only NUMA or NUMA as well?
Okay. OpenCL is
Going to support only NUMA as well as NUMA with
NUMA with?
uniform memory access.
Oh, okay. See, it is to answer your question. OpenCL is not tied to a specific architecture. It is not tied to a specific architecture. So if you see this previous slide, right, it sees different computing unit, regardless as a NUMA or if you have say vector engines or just plain simple processing units. So all of them, irrespective of architecture, this is treated as this architecture model. This is the model it is going to use. So if you have a NUMA in place, right? So for that, it will take, assume there are 4 processors aligned in a NUMA format, right? And its own local memories. So for the OpenCL, it is 4 processor becomes compute device 1, 2, 3 and 4. That's it. And each of the individual shared memory of that processor will fall into the global memory of each of them. That is how it works. It is not going to tie up with any of the architecture. It is architecture dependent and independent. Any other questions?
Sir, you said that each compute device is equal to one graphics card.
Okay, let me take. Okay,
It's
okay.
equal to one graphics card.
Yeah.
So how about the cores? Like you have dual core, single core, and quantum.
Yeah.
So do you mean to say that when you add number of computing devices, will it increase the capability of the display or?
Okay, see, it is what we are trying to achieve is see each compute device. If you take graphics card, right? So it comes with its own set of accelerator, say video decoders, then assembly engines, right? Array of assembly engines, and you can support the SPM, single program multiple data, which CPU cannot support that. So what is that? I can tell you what is that single program multiple data, right? Probably you have heard of single instruction multiple data, right? So the graphics card can provide support that. So what happens is the graphics card has its own capability. So you are programming, you know that capability, and you are writing the program to use that capability. Okay. CPU has its own capabilities, which graphics card cannot replace. So for example, in terms of sequential execution, so or you have a task parallelism, that's what we call it as task parallelism. So that cannot be replaced. Say you have a sequence of decision making, control flow that cannot be replaced by a graphics card. So there you need to use CPU. Okay. Now you have a number of cores there, right? So here, from the OpenCL point of view, OpenCL view. So OpenCL doesn't see it is a CPU or it's a graphics card or it is a different thing. So for OpenCL, it is a compute unit. That's it. So you can, if you know that this task is data intensive or graphics intensive or some other thing, so you can redirect the workload to the GPU, or this cannot be done by GPU, So you have to redirect to CPU. So OpenCL provides this set of options. It is the user who is going to, the programmer who is going to decide where it can go. Okay. So by adding more cores, you are getting performance. I cannot say that unless you decide and make it happen.
No, my question is, if you add more number of computer devices, graphics card, is it like, let us say we have a single core.
Okay.
So single core and one graphic device.
Okay, fine.
So it is working fine, let us say. When you have dual core and if you have two graphic cards in it.
Okay.
So there is no match as such at all. It is nowhere related with the graphics cards, how many are going to place and the core architecture.
Yes.
So do you mean to say that even if I have quad core architecture and with one graphics card, so there is no relation as such and it works fine with even with one computer device?
Yes. Should work because that is what OpenCL is taught, says that. Right? So any other queries?
So I'll add a point to what she said. It's like you're having a 4-core system. Assume like you have a dual core server which has 2 processors. One is a quad core, another one is a dual core. Okay, you have 2 processors, total 6 cores. And you have one graphics card, which is like 200 teraflops or whatever it is, like say 2 teraflops double precision. And you have one sound card attached to your system that has some calculation power. And you have some embedded system connected to the network. Everything will be calculated, code will work. So you can decide where you want to run the code. So the idea is it has to work in everything. That's why OpenCL has come up. So it will work. Performance is not guaranteed. You have to tune it.
Thanks. Okay, I just said something about SPMD. This is the only thing, I think you have heard single instruction, multiple data. What is SPMD? Single program, multiple data. So it's just like on the graphics card, what you can do is, you can run a program. That program has a condition check. Say one is the if part, the one is the else part, right? So what happens in the CPU is, so it can do a branch prediction and take the path. It will predict. It's not actually happen. It will take the path and start executing. If it finds that path is not correct, it has again to roll back and it has to take back the path to go with that. What happens in single program multiple data? It executes both the if and else part. The program, not the simple add or sub, a complete program is executed. So one of them gets false, so that part is just left out. Want me to explain once again? Yes. So you take a graphics card, okay? You have a program which contains an if and else, so true and false areas. So if it's in the CPU, either one of them will be executed, not two of them. In graphics card, both of them can be executed, will execute parallelly. So, but both cannot be true and false at the same time, right? So one of them will become true. So whatever the condition is true, that part is just taken up. The other part is just ignored. So that means you are not having you will not lose time just making the decisions. In case of CPU, you have to roll back to the condition which has become true, or you have to wait till the condition becomes correct. In this case, just execute parallelly both true and false, the same complete program, and one of them which becomes false is just left out and taken the path which is. This is possible only in the yes. Next is your OpenCL program structure. You have two parts in the OpenCL. One is the host program Other one is the OpenCL program. Okay. The host program is the one which runs on the CPU, your native CPU. Okay. The OpenCL is the module. So I will not call this as a module, I will call this as a kernel. Okay. This is a OpenCL kernel. You have identified that this part of the program or the module kernel should execute in OpenCL compute device which you have told, which you have identified. Yeah. So the host program. So it contains series of steps that are there. So I'll just categorize three of them. You have something called the platform layer. You have set of APIs. OpenCL contains set of APIs, right? So the first API is your platform API, runtime API, and the language API. So this is the set of program structure. So what is this platform API is all about? So you have, say, in front of the box you have so many computing graphics cards are placed, the CPUs, the DSPs are there. So you need to, if you have written a program and your program needs to identify how many, means where to run. So it needs to identify what is the OpenCL compliant devices available there. So there is one API, simple. It is like, how many of you have used system command in your system command, your C program? Printf. Okay. So what I'm trying to say is, printf is simple. What I call is an API, which is used to display stream of characters on the console, right? Likewise, you have API, okay, to query the compute devices, set of APIs. So it's like this. You have, say, CPU, graphics card, DSP. Okay. So I am the CPU. I am the OpenCL program. What I need to know is how many devices are there. The program should run. So I should call an API to identify what are the OpenCL compute devices. So first API is query the compute devices. So I got the information. Okay, I have three compute devices. Now what I do is, you should see the program is what? Program is what? Set of instructions under. Okay. What is process? Process. It is under execution stage. So how to make it execute in the execution mode? So you have to create a context for that. You have process context. So process context is nothing but contains the data, then the instructions, right? The stack, the heap, all this becomes your process context, right? So now what you have to do is, you have identified the devices. Now you have to create a context so that your kernel will go and sit and run there. So you have an API to create a context. So create a context. So you have created a context for that. Then what you have to do is, you have to create a memory spaces. So what is the memory spaces? If I say int a, what does it do? So it would have allocated a space for the data type, say maybe 4, 8 or whatever the size based on that. So likewise, you can create a memory objects associated for the OpenCL. So one is compute, create a context, create the memory objects. Next thing what you have to do is, you have to get the kernel and place there, right? Okay. Now comes the interesting part. The OpenCL kernel, whatever you see, there are two parts. One is the host program and the other one is your OpenCL kernel. The OpenCL kernel can be of two formats. One is, you can just give a simple source as is, what does it do is, at the run time, it will compile the kernel and generate the code. That is one way. It will take the source code at the runtime. Your host program is running. Okay? At the runtime, it will open the source code of your OpenCL kernel, take it and compile it, generate the code, and pass it to the command queue. Okay. Something different. So this is called runtime compilation unit. This is called runtime compilation unit. When the program is running, your host program is running, but your OpenCL program is getting compiled at the runtime and getting assigned to the task queue of OpenCL task queue. Okay? That is one way of doing it. There is another way of doing this. So that this is also called as online compilation. This is also called as online compilation. There is another thing called offline compilation. What is it? Offline compilation is, say, if somebody, see, when you are developing a code, you don't want to share the source code, right? Then you have to give only objects, binary objects. If that is the case, then what you do is you create an offline binaries. Create an offline binary object, compile it before itself, and pass it. So the same thing happens in both the cases. So it creates the context, creates the memory. At this point, it just opens the binary file and passes it to the command queue. There's nothing like compiling at that stage, right? So you have some set of APIs which is responsible for attaching the kernels to the queues. So you can do that by yourself through an API. See, there are 3 compute units. So you can take this kernel, assign to this compute unit, queue. So like that you can assign it. So once you assign it to command queue, it is understood, it's like dispatching the task. It is now the compute device, take it and execute, that's it. It's not your job. So it's once done, you have something called synchronization commands, APIs. So you can have this task synced up. Okay? Then this becomes the runtime part of APIs. Okay? The last part of the API is your kernel language. See, when I said there's a runtime compilation unit or online compilation, somebody has to be there to compile, right? Who has to be there to compile? There should be a compiler. Yes. So if there is a compiler, there should be someone to understand the syntax, parse it, generate the code, the binary object. That is given out by the language APIs. That is taken care. You don't need to worry about this because this is internal, right? These things probably you should know, but this is internal because it takes this APIs takes care of. It is based on C99 standards, so which takes the syntax of that and it takes care of your compilation. So up to this, is this clear? I mean, any queries you have to go with?
We have told that there are 2 ways of building program objects. Online compilation, there is a performance penalty?
Actually, that's a very good question. Very, very good question. You have the offline compilation and online compilation. The same question is raised time and again in Java also. In Java is also like this. You have virtual platform layer. It's a hardware. Everything is virtualized, and the source, the bytecodes, translate bytecode is converted into native. So you have something called JIT, just-in-time compilation. So that part is again pushed into this, into the OpenCL. So that is that takes care of your performance gap. So Any other queries? Okay, just to go, I have listed out a sample OpenCL APIs. It's a very, I'm not added in to keep it simple. This is your first hit at OpenCL, so it should not. I will just remove all the arguments to keep it very simple, because the idea is to understand the usage of it, the purpose of that APIs. Usage, you can always open the manual and you can just check out what is the way it can be used. So I said you have to get there are a set of APIs. So platform API, get the query the compute devices, create context. So likewise you have, starts with CL get platform IDs, CL get platform info. In your host program, when you are writing a program, in your host program, you have to add all this, because the CPU will execute this and it will identify how many OpenCL devices are there. Okay, so you get the platform info. Okay, after getting the platform info, you can create a context, right? Then I said there's something like you have to compile and create kernel program objects. So how do you do that? Build program, right? So you can get the program, then build the program, then you can dispatch it to the task queue. Then you can get a device info. Once the program is complete, you can have a release the program and clear the point. This is a cleanup activity. So it will release the program and release the context. And just listed out to know how an API will look, how the API will look together. So up to now, is this clear? I mean, things how it's. So then we can just see some sample programs and okay, before going into this, I just want to ask you one simple this thing. Since all of your faculties, operating system, in the operating system, you have process management, memory management, the IO, device management, then file management, right? Then the task queues are there, right? Resource management. The beauty of OpenCL is, see, earlier all this stuff was completely hidden from the programmer. Programmer was need to depend on what is the performance that OS can maximum give. Now all these are exposed through APIs. This OpenCL, you can create a context, query the device, you can lock the device, you can redirect that task to this device, right? What exactly you are doing is what exactly the process management of the OS. So a programmer can now tune his entire application to the peak performance. So this is one thing which I'd like to tell you. Okay. Okay. I just this is a sample OpenCL program. Yeah. Okay. That's okay.
One size small.
This is a starting program, so I'll reduce as I take it up. So this is a allo. See, I mentioned you two things. The OpenCL program has two parts: the host program and the OpenCL kernel. So you have to write the OpenCL kernel. So to do that, you have something called HelloCL. This is sample program, kernel program I just listed out. It doesn't. This is actually dummy stub. Dummy stub means it is just creates a context, goes to the device, comes back. It's not going to do anything much more than that, right? So here, all the OpenCL kernel is stack underscore kernel, and the file name will be the extension .cl. .cl is extension, and all the kernels will be underscore kernel. An interesting point to note is, generally kernel sizes will be very small. It's not that you have to make it small. As you start programming in OpenCL, you find that the tuning part will be the smallest part which can get you the maximum performance. So going by that, so your OpenCL kernel will be always a bit small, it's maybe 100 lines, that's max, that can go. So coming back to the host program, in the OpenCL, whatever we are having, we have two parts. One is you can call the APIs, just whatever OpenCL APIs I provide, you can call directly the APIs, or there is a C++ wrapper around it, so that it can be easily twisted and bent, so that easy for the programming aspect. So whatever I am showing you is the C++ wrapper to that native calls, right? So from the next example, you have the actual APIs we see. So what you have to do is you have to map whatever the API I just showed you with the C++ wrapper. So in this case, the first, this is the header file that you need to include for your OpenCL programming.
What HPP stands for?
Sorry?
HPP.
Okay, it is header file for C++. HPP. Like .h for C, we have .hpp for C++ header file.
C++ header file.
Yes. Which contains all the definitions, the API entry points.
Are you all surprised by HPP? Then you are new to C++. Yeah, actually we start doing real world application. You need to call a lot of headers.
Yeah, true. So another thing is, since a lot of things are in open source, people come with their own set of approaches. So you have not, see, like for C++ extension file, you have what capital C, CPP, so many ways of expressing. So I mean, this is another way of doing this. So what you do is, here we are creating a simple object for the platform to get the platform information. So this actually calls that CL and get platform. Okay. So once you get that, so it returns the error value. So once okay, it is successful. Okay. What you have to do is, see, there are multiple platforms, right? Multiple platforms and multiple compute devices. So what you can do is, you can query each of them and get the info for that. So you can have different platforms altogether plugged in. So for example, in this case, if you have AMD graphics card, the 5X series, then 6X series, then you have different kinds of platforms. So each of them can be queried, and so that you can, so why you require to get platform information, or why do you require to get the platform information? Yes, that's the exact point which we have to report for, because we need to know what is the capability of the device, then we can actually use it. So before locking that, what we'll be doing, then what you do is create the context. So this property or this object, you can use it for create a context. In this case, can you see this underscore CPU? So in the first question, can the host CPU be the OpenCL compute device? Yes. If you want to do that, you can say underscore CPU. So that means your host CPU becomes a compute device. If I put underscore GPU, so you are locking the GPU, right? That's the way it goes. Then what you do is you can get the device info. Get the device info for that. Okay. Then this is a place where we are trying to get the sources. See, once device info is ready, what you do is so context is created. Now get the source. Source of what? Get the OpenCL kernel source by using this, and use this program.build or CL build. Probably I'll just open that slide. So we had something called program build. So this API will be called. So it is going to build the program. So you may ask, why is it required to build online? Why is it required to build online? Probably we could have built offline.
On the fly you can do some changes.
Yes. So the code is not fixed. If I have generated the code, then either it will be generated for CPU or GPU. I cannot move around. So now I can quickly move around. So code is not fixed. So if there is another card has been placed, so when you run this, it will compile for that card and generate the code for that card. That's the beauty of online compilation. Okay. So then program build. So remember, program build will be using the C99 language APIs. This is a C99 language API. So now you are taking this kernel, okay, and there is a command queue. You remember in the operating system there is something like task queue, right? The task queue is you take the task and put it into that queue, so it will be serviced or executed on the CPU, I mean the clock cycle, means the time slice. Here you have a command queue space for that. So each context, whatever, see, right now you took that program and you have compiled and you have put in the context. So if the context is ready, what you do is you take that and assign to a task queue or the command queue. So once you do that, it starts executing. You don't need to do anything further. Okay. once done, so this will take care of that. So in this case, see, we are specifying ND range 2, 2. 2, 2 in this case, you have how many? See, you have specifying the range of, see, 4 into 4. So you have, yeah, or 2 into 2, 4. That's how it is mapped. And this forms the cleanup aspect. The cleanup aspect is this, the CL release program and the release context. So I'll just run this. How do you run this? What compilers do you require? Right? So you require to install EMP provides a APP. So SDK. So you need to just accelerated processing, parallel processing SDK. So you can just install that. Then what else you require? So you can use, the OpenCL as of now it supports, the support is provided for Windows platform and Linux platform. So for Windows platform, if you have Visual Studio, you can just use that as your post-programming compiler. Or if you have Linux, you can use a OpenCL compiler or a GNU or toolchain, whatever compiler you have, so that you can use. So what I will do is now, I'm using this in Visual Studio 2010. Okay, I installed that SDK. So just begin the solution. Since it's up to date, it's not reading. So if you can see that, just try to maximize. Is it visible? Sure. So what does it say is, it's an OpenCL program. So what it does is, it tries to initially get the platform information, then it creates a context for that platform, then getting the device info in that platform, and loading this CL. Right now we had a dummy stuff. Okay, it doesn't anything. We'll take that, compile it, run it. Once it's clear, just comes out. Okay, probably you'll find, right? You have written so many programs, hello world program, you'll find that is the easiest one, right? Writing a simple printf, hello world, done. This writing the starting program looks pretty much takes time, but once you get hang of it, because it's the same, you know how the OS, the task queues, how you can create the context, things like that. So you can easily write your own programs. Okay? So this is a simple allow. So you have any queries in this?
Sir?
Yeah.
So like you had mentioned one line there, underscore CPU. You said that underscore CPU, so you're blocking the particular part of
Yes.
CPU. The same way if you are blocking the GPU,
Yes.
and at the same time at my backend say I'm running a HD video or something.
Okay.
So like it is using my GPU, plus my program is also using the GPU. So will the synchronization be implicit, or the programmer has to take care of it?
Oh, okay. That's the interesting question. See, this is a context. as we know in the operating system, it is a security is enforced within the context. So your video encoding, decoding, whatever is happening for another application is totally isolated from this and that. It's a totally two different things that the operating system should take care. So that is not going to affect anyway. So any other? That's interesting, very interesting.
So when we create command queues, we create a separate command queue per resource.
It's a good one. Yes, you can have multiple command queues per resource. That's why we can assign different. When you have the kernels compiled, you can assign each of them to different devices, and it takes care of it. Anything else? Okay, then we'll go to the next one.
When you said underscore CPU, you're not specifying which core to use, right?
No.
Is there somewhere specifying which core you want to use?
Okay, I'll tell you, I'll come to this example. From this example, will answer your question. Means, see, what the OpenCL says that is, so you have the architecture, what do you say, it is being masked, the architecture is being masked. You know the capabilities and you are just saying that, okay, use this compute device, right? So if there is, say, 10 calculation that has to happen, and if there are 5 SIMD cores only, okay, then probably that will be taken up as 2 into 5 because you have assigned for that CPU, but CPU doesn't have that capability, but still you have to attach to execute. The OpenCL guarantees, that's what I am saying. OpenCL guarantees the functionality with may degrade the performance, or sometimes it may improve the performance. It is a different thing, but your the CPU will take, or the OpenCL will take care of that part. That's what I can say. Okay, the next interesting thing which I can, this is the next interesting program. Always it is, do you want to find what is the capabilities of the device? One way is to go to the manuals, the sites, things like that. The other way is write a program, print it out for you. So it will give the complete list of info, what the hardware is capable of. Okay? So I just run this. Okay, this is a okay. This is a simple. Okay, currently, right now, whatever this laptop is, right? That's an APU version. That is CPU, GPU fused together, fusion product, and it is a AMD E350 model, right? So it says what is the cache type? Okay, what is the cache? Line size is 64, cache size is 32K. What is the global memory size? So you can get all the information, technical information about your compute device, right? So it gives set of APIs. So what is the API which we were referring was? If you see this API, get device in. So that will take care.
Usually when you optimize, you take a printout of this. When you try to group your kernels, this create useful information. Okay.
So there is something like image processing example, Gaussian noise. So right now all these programs are run on GPU. So it is running on the device 0, lowland. Doing one iteration. Okay, there are two. This was the input file that was being processed. Okay, we'll see the output how it does. This looks after that noise. You're introducing a noise, right? So you can see the noise, pixelated noise. See the clarity here, right? Right? This is a run on the GPU using OpenCL. Okay, there's one. I'll just show you one more interesting one. Okay, we are till now what we are saying is we are talking about only the GPU is always meant for we are showing in terms of graphic processing, either video decoding or sound processing, right? There are capabilities which can be seen for binary search. So that means you can use it for your searching, sorting, right? Techniques. So if that is applied, so I think you know pretty much everywhere searching sorting is used. That's it. Minimum base thing. So you are now using not CPU to do that, you are using GPU to do that. This is a simple binary search. There is something like Floyd algorithm, Warshall's algorithm that's also been written. It's doing that. See, everything is running on the some result. So this is about your. What I'm trying to show you is what are the this is an interesting one. Advanced encryption standard, which is used for. So I'll just run this, and I'll show you how your advanced encryption standard can also be used using this. So I just generated a RSA key and it's doing the processing, and it is generated output as some what this program is doing, the advanced encryption standard. It takes an input file, it generates row-wise, column-wise, it generates a key, then uses that key to manipulate row-wise and column-wise bytes of information and generates an encoded form. So the input file was this. This was the input file, basically, and this is the encrypted version for that. So now we are not using CPU to do that, we are using GPU to do that. Okay. What I am trying to show is where and all the OpenCL can be used along with your hardware capabilities. So there's a Freud and Marshall's. I take this. This is an interesting one. So yeah, this one I'll explain because this is. Okay, this is a simple program based on OpenCL. Okay. I'll just run this, then I'll go into that piece of code, how exactly it is being done. Second is, so this is being run on the GPU. Okay. So thanks. Okay, I'll just run through this piece of code, how exactly this is happening. This, okay, and this is the font size. Fine. Okay. So this is a simple kernel which is generating a sine wave format. So what you are doing is this part is you are calculating the coordinates for that generation of the sine wave, and so for each pixelate, the one which we had shown. So this code forms the core part of your kernel. So this will only execute in your GPU, right? That is responsible for generating the points on the screen. Okay, I'll just take this as this one. So what is it doing is, so what is the first step you are supposed to do? Okay. Yeah, you have to query the platform. Because see, for the host CPU, it doesn't know how many graphics cards are there or how many compute devices. So there's no info. So you have to get that info in your program. So for that, so that's what we are doing. Queries? So we are doing this. So you're getting the platform. That's a API for getting that info. You're getting the platform IDs first. Then you get the platform. For each ID, you get the platform info using this API. Once done, what is the next step we are supposed to do? Create a context. So that's what we are doing here. Then once context is created, so there are cases where you okay. So you are okay. Create program with source, build the program, CL build program. Okay. get the program information. Then what is the next step you have to do when everything is ready? Dispatch to where? Command queues. So, in this case, so we have create command queue here. So create the command queue, then assign that to the command queue. So finally you have an API which is used to clean up. You have something called CL release mem object, CL release kernel. So these are all release program, release context, release command. These are all the release cleanup APIs that you have. So this is the holistic view of different examples where how you are different areas. It's not just examples where OpenCL using the GPU accelerator, you can actually program or increase your performance of your application. Okay. Coming back to the slide, I just wanted to give you a demo. See, it's like this. Now you have learned the OpenCL usage and you understand how OpenCL gives the benefit. We saw that the only small piece of code is just part of .cl file. Why is that only the small piece of code? Why not entire program? Right? Okay, the other question is, how do you identify that small piece of code? You have in a real life application, you have thousands and thousands of lines of code. In that, how do you identify this piece of code is the one which is need to be tuned? So now I'll just give a simple demo tool called Code Analyzer. This is also available in the AMD developer website. You can download it. You have two versions. One is for Windows, another one is for Linux. Both, means whichever is comfortable, you can. So since we are in the Windows platform, I'll give a demonstration how you can actually use Code Analyzer for a real life application and identify the hotspots. Identify the hotspots. These hotspots will go into that .cl file. Okay. So I'll just give a simple demo. This is a Code Analyzer. So using this you can find the hotspot that can go into your .cl file. It's very simple to use. What you have to do is create a new project. So I'll say demo project. Okay. Now the next thing is, see your application, you have a program that needs to be tuned. So in our case, I'll just take an example, an Internet Explorer. I think that's you can take any of the applications. You want to take a Microsoft Word, or you want to take a simple, which is the video player we normally use? VLC. You can take a VLC player. run that player, right, and identify the hotspot. So right now I'll do it for Internet Explorer. Okay, to find the hotspot in the Internet Explorer. So this is the application. So what I have to do is I have to open so what I have to do is I have to open the code analyzer, create a new project, identify the browser and identify which application need to be profiled. So just mark it. There's a work directory, you can specify that. And you have other set of options that can be used. So there are various ways of doing profiling. You can do instruction or event-based profile or the time-based profile. So for a convenient purpose, I'm showing you time-based profile for 20 seconds. This profile works for 20 seconds. So I'm selecting a time-based profile. You have a series of profiles you can select here. Okay. Then that's okay. You see, there's a start button here, right? On that. Now just watch for the 20 seconds. It's launched an Internet Explorer has launched Internet Explorer, and it starts profiling it. I know it's already. Yeah, see? The Internet Explorer has been launched and is being profiled for 20 seconds. So it is done, the profile. Why I'm taking 20 seconds is just for a demo purpose. So if you want for a higher resolution, you do it for 1 hour and practically you start browsing and doing things as a normal activity. You don't need to do anything because this code analyzer is not hooked into that. I mean, it is not going to affect the way you are working. You go on working your browser normally, right? The backend, it will be monitoring all the code, how it is being, the code behavior. So once done, see you got the profile of with the percentage of time sample. What is the highest taken is some kernel.exe. So we don't want that one, that's a system process. So what you are interested is, I'm interested in IE.exe. Just double click on that. So I gives a list of things which has been taken. Double click on that. So you find list of APIs within the module which has taken. So you take the highest one. So you can find the list of this is assembly of your Windows. See, as simple as just click. Now you have a hotspot. You find this is a hotspot. So a series of hotspots, and that's the peak one. So if you have compiled your application with your debug information, if you have done, I think you understand, right? -G. If you have compiled debug information, because this Internet Explorer is in a production environment, it doesn't come with the sources. So if you have a application, compile debug information, do the same thing, it will give the source lines just above that. So you know you can go back to your application source and see, okay, this part of the code has taken more time. So that becomes your hotspot. So now what you can do is you can take the hotspot, convert it to a kernel, move it into the .cl file kernel and put it to OpenCL and run the same application, and you see the difference. So even the IE9 or Microsoft 2010, whatever you are getting, so all of them would have been fine-tuned like that. So you are not be expecting .cl file there because it's closed source. Probably you will be having binary files to go with. Okay. So this is how you do that. So now, now you have complete end-to-end. End-to-end is what? End-to-end is okay. I'll come back to the previous slide for this. So now you have an end-to-end. What is the end-to-end? So you have the tools, SDKs, download that, take a code analyzer, find the hotspot, take the ABP SDK, port it to OpenCL. Okay. Now you have a kernel. Okay. That is fine-tuned. Now the next question is, without actually running this kernel, can I know the performance? Without actually running it. So for that, we have something called Stream Kernel Analyzer. Okay, this is an interesting tool because you don't need to compile or you don't need to run the application and see whether what is the performance you're gaining. So this is a simple code. What I'll do is this. This is the code which we have seen in the OpenCL simple GL example. I'll say compile. What you do is you take the .cl kernel code, copy it into this window and say compile, gives out the assembly. Okay? And just below that you can find list of graphics cards, their capabilities, and it says how many ALUs are there, what is the time, what is the estimated cycles, how much time it is taking for fetching, and what is the bit clocks, and what is the maximum throughput you can get it from that kernel. So now you have the kernel without actually moving, you know the performance, which is the best one. So if you know which graphics card you have, you can quickly tune it for that. Or if you are planning to buy an additional accelerator, based on this, you can go with that. This is a sample result which I just pulled out from an IEEE paper, which was published in 2009, and which talks about OpenCL used in embedded profile prototype in mobile devices. What does it do? It is doing a processing 100 frames, okay, of 32-bit RGBA of this resolution. So it's a simple stuff. If you are using processing this, if you have one CPU, one GPU, processing alone, it takes frames per device. Say if the CPU is processing 100 frames, so you can find the execution time is around 846. That's average around 8.5 seconds per frame, right? So this is a min and max. So we just forget about this min max as of now. So if you are doing the same thing in GPU, you are doing 100 frames, the same 100 frames, it's just taking 240 seconds, and you have the entire thing completed in 2.4 seconds only per frame. Okay. Now we will see the APU aspect. If you are using the heterogeneous computing aspect, if you have CPU and GPU together computed, so what does it do is CPU will do say approximately 19 frames and the GPU will do approximately 81 frames. So you find that on the average, the CPU takes 12.5 and GPU takes 2.1 seconds. So on the average, you have within 2.5 seconds, your computing is completed. So if you use this combination, this is best. You may ask, this was best, right? 0.4 or 2.5? 0.4. The point is, when you are going with this, you are getting the performance with the power efficiency. This is the embedded side. You cannot run full throttle anything. I just gave an example of a supercomputer, of the T1A, which saves almost 8 megawatts just by going to heterogeneous computing. So this is a simple example. Now you can. There are other set of IEEE papers listed out on OpenCL. Okay, what is the final takeaway? The final takeaway is students, new tools and new directions and new approach for programming. That's the first thing. And all tools are available in the site, and you can have videos, complete thing. You can get. You can learn by yourself. What for the faculty? Faculty, it can be used for paper publications because, as I see, we are close to maximum 57 to 60 papers only listed on OpenCL till now. That's very small amount in this case. So you can use this OpenCL for research domain. I think you can be the change. So this is a site. You can just go and get all the resources which is required. Right? If you have any queries, Q&As,